So starting with the chemical shift. So item 1, chemical shift Hamiltonian. And let's respect Mr. Hamilton and put a capital H in here. Standard treatment from the very beginning, right? So the energy is minus mu dot B. Our magnetic field is on the z-axis, so that is minus mu z times B, and we called it B naught to emphasize that that is our principal superconducting magnet. And then the corresponding Hamiltonian is obtained by replacing the magnetic moment here with the corresponding magnetic moment operator. So our H is going to be minus, then mu z is gamma s, so gamma, say, of the protons, then sz, then times B naught. And finally, minus gamma B naught is the definition of the Larmor frequency, so omega sz. And we have seen the matrix representations of these operators for a single spin in the previous lecture. So let us now consider two things. Firstly, we will go from an idealized situation where we just have a proton sitting somewhere in vacuum and not interacting with anything, to a situation where we have interference from the local electronic structure. And as you chemists know, we have the concept of the chemical shift because to some extent the nucleus is shielded by the surrounding electrons. And so what we in practice have here is not just this, we also have a correction term. So practice is minus gamma and then 1 plus delta sz B naught, where delta is the chemical shift. And if you remember your chemical shift scale, it's easy to rationalize physically various situations where you have electrons pulled away from an atom, carboxylic groups, aldehydes, where there's little electron density on, say, some hydrogen because there's an oxygen nearby. You remember that the chemical shift was large, like 10 ppm. If we put 10 times 10 to the minus 6, so remember part per million here, this frequency overall, omega, will become larger, and this is because there are fewer electrons around to screen the magnetic field, and so the Zeeman interaction stays a bit stronger. In a situation where we have a lot of electron density on the hydrogen, in lithium hydride, for example, or in various paramagnetically shielded situations, remember the chemical shifts were small and sometimes even negative. So what that would mean is that this will relatively be reduced. The Zeeman frequency is reduced. This is because the nucleus interacts somewhat weaker with the magnetic field because it is screened by the surrounding electrons. But ultimately, this minus gamma, this correction term, and B naught is just an updated definition of the Larmor frequency. Okay, let us look now at the Hamiltonians in situations where we don't just have one spin, but we have multiple. For that, I need to introduce a little bit of extra mathematics. So there's an item A here, Kronecker products. After Leopold Kronecker, a German mathematician, and let us consider a situation where we have two spins. The first spin will have two possible states, alpha and beta. The second spin likewise. And so the combined state of the system will be alpha alpha, alpha beta, beta alpha, and beta beta, right? Every possible combination of spin up and spin down. Turns out, and Kronecker recognized that operation early on, that such combinatorial relationships in mathematics are very common. And the definition of a Kronecker product between two matrices, or as in this case two vectors, because a vector is a special case of a matrix, is if you have a matrix A Kroneckered with a matrix B, what that means is that every coefficient of A, every element of A, gets multiplied by the entire matrix B in the following array. So it's A11 times the whole of B, then A12 times the whole of B, then A21 times the whole of B, A22, B, and so on. So this is, of course, a bigger matrix, but you can see how it combines A and B in a combinatorial way. So we have every possible product between every element of A and every element of B appearing somewhere here. And that is a special case of such a relationship. And the final thing that makes these formalisms really useful is that A cron B times C cron D. So if we multiply together two Kronecker products of the same topology, meaning that A has the same dimension as C and B has the same dimension as D, then this is AC cron BD. So when we multiply crons together, first term here multiplies first term there, second term here multiplies second term there. In quantum mechanics, imagine now that we would like to have an operator that acts on only the first spin and does not act on the second one. In this four-dimensional representation here, well, goodness knows how to make a matrix that only influences the elements of the first spin but not the second. But these Kronecker product relations allow us to do that. We then realize that an operator that would act on the first spin and not act on the second would have this kind of structure. It would be some kind of matrix, 2 by 2, Kronecker unit matrix. When we multiply this by this, A will be multiplying this vector and something will happen to it, and 1 will be multiplying this vector and nothing is going to happen to it. So one of the easiest ways of building multi-particle Hamiltonians, and this is in fact what modern computers are using, is to build them using these Kronecker products. So with that in mind, let us think about what a two-spin Zeeman interaction operator is going to look like. We have a Hamiltonian, then the first spin would have its own chemical shift and its own frequency, and let's call it omega 1, then S, Z acting on spin 1, then omega 2, and then S, Z acting on spin 2. Well, because we have two spins, we have 4 quantum states in the system, so these matrices will be 4 by 4. We will write down elementary matrices, so the ones without the indices, somewhere here. So Sx is 0, 1/2, 1/2, 0. Sy is 0 minus I over 2, I over 2, 0. And then Sz is 0, well, 1/2, 0, 0 minus 1/2. Now these are Pauli matrices of a single spin, but these needs to be selective. So the first operator must be acting on spin 1, but not on spin 2. And so W1 Sz Kronecker unit matrix plus then here must act on spin 2 but not on spin 1, omega 2 unit matrix Kronecker Sz. And let us now explicitly calculate that and find out what that 4x4 matrix is going to look like, and that will give us the energy levels of a two-spin system in a magnetic field. Okay, so the first matrix going to be big, SZ Kronecker 1. So we need to take elements of SZ, which are here, and we need to replicate the unit matrix. And let's put it here just so that we have something to refer to. 1, 0, 0, 1. And let's do that. Okay, SZ, first element times the entirety of the second matrix. So it is 1/2, 0, 0, minus 1/2. Then the second element of SZ, say this one, times the whole of that matrix. So 0, 0, 0, 0. Then likewise here, we have 0, 0, 0, 0. And finally, minus 1/2 times the remaining element of the unit matrix. So we have, that should be a plus. And then that's minus 1/2 minus 1/2, 0, 0. Times this frequency, omega 1. Okay, this is our first term. Let's get the second one, then add them together and take a look at the physical meaning of what we obtain. So plus omega 2 times. Now it's the unit matrix that sits in the position A. So we have to take every element of the unit matrix and multiply it by the entirety of SZ. So we are going to have 1/2, 0, 0, minus 1/2. Then zeros here, and then again 1/2 minus 1/2, and zeros. Notice how relatively straightforward such operations are. We just map arrays and multiply them by each other. Our alternative would have been to calculate these Hamiltonians element by element by taking inner products of these states with the corresponding spin operators, remembering their elements. You have probably built some angular momentum operators that way. That is exceedingly boring. So this Kronecker structured arithmetic is the more modern and somewhat easier to use version of magnetic resonance theory than the one you will find in textbooks, where you literally just go element by element and calculate them that way. Okay, so our job now is to combine these two matrices, and of course you can see the matrix is already diagonal, so those are our energies. Let's first take a look at them, plot them, and then they will come handy when we start dealing with the J-couplings. So the top level, omega 1 plus omega 2 divided by 2. Then 0, 0, 0. And the second level is omega 1 with a plus, minus omega 2 over 2, 0, 0. Then the third level, minus omega 1 plus omega 2 over 2, and then 0. And the final level, 0, 0, 0, minus omega 1 minus omega 2 over 2. Let us draw them as energy levels. Let us assume both numbers are positive, which would be the case for electrons, for example, or nitrogen 15, where the magnetogyric ratio is negative. And look at those energies. Okay, so omega 1 plus omega 2 over 2 at the very top. Then we have omega 1 minus omega 2 half. Then I will draw them unevenly spaced because the two frequencies needn't be the same. So minus omega 1 plus omega 2 over 2, and finally at the bottom here minus omega 1 minus omega 2 over 2. And this would correspond to the 4 states that we have here if we have that as our first spin and that is our second spin. So that is alpha, 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 beta, beta, alpha, and beta, beta. And let's take a look at the corresponding transitions. We will draw the transitions of our first spin with the yellow marker and the second one with blue. So the flip of the first spin, alpha to beta, that. And you can see the energy difference between this. If we take this and subtract that, omega 2 subtracts out, and you get omega 1 over 2 plus omega 1 over 2. So this energy level difference is exactly omega 1, as you would expect. Let's draw the label on the other side to make ourselves some space. There. Likewise, we have a flip from alpha to beta here, so that is also omega 1. Transitions of the first spin. For the second spin, we have alpha into beta, that is here, so omega 2, and then alpha into beta here, that is omega 2. And you can see that we have chosen our spins in such a way that the omega 1 is larger and the omega 2 is smaller. So as drawn, this is perhaps proton and phosphorus. And if we draw our transitions, so that is the absorption amplitude of the electromagnetic radiation, we will have our blue transition somewhere here as a function of omega, and our yellow transition somewhere here. And they overlap, right? There are 2 transitions with exactly the same energy, so they will be exactly on top of one another. That's omega 1, that is omega 2, and the axis is our frequency. So far, we just have 2 spins that are sitting in that magnetic field, not doing much and not interacting with each other. These are just Zeeman energy levels and Zeeman Hamiltonians. So item 2 is to get them to interact. So 2, J-coupling. Let us first think in general, going back to the previous lecture, how a pair of spins would interact. They are magnetic moments, so they interact firstly directly, as 2 magnetic dipoles would, but that interaction is anisotropic. It is directionally dependent, and when molecules are tumbling rapidly in a liquid, it is essentially just averaged out in much the same way as if you take 2 magnets in some orientations they attract, in other orientations they repel, and if you take every possible relative orientation, actually the interaction energy averages to 0. J-coupling is a different beast. It is the nucleus interacting with the surrounding electrons, slightly polarizing them. I'm simplifying somewhat, but that's the general idea. And then that polarization propagates through the electronic structure and interacts with the other nucleus. So this is an indirect interaction through the electronic structure. And it has a relatively simple form. H J is 2 pi j, and the reason there is 2 pi here is, again, blame the history. In magnetic resonance, J-couplings are always measured and cited in hertz, and in quantum mechanics, of course, you know that we need radians per second, so this somewhat unusual 2 pi is just stuck in the formalism across every textbook you've ever seen. And then we have, let's call these 2 spins at this point, not spins 1 and 2, because if we do that we will just get swamped by indices. I will call them L and S, so between L and S. So there will be L, Z, S. Z plus Lx, Sx plus Ly, Sy. You can see it looks just like a scalar product of the two spin direction vectors. There are two limiting cases here. If we deal with nuclei that are close in frequency, like two protons, then we have this entire Hamiltonian. Every term contributes, and that is called a strong J-coupling. If we have two nuclei of a very different type, so or a field that is sufficiently strong to separate their frequencies widely, then the XX and the YY term, well, consider what they do, right? Remember, both nuclei precess rapidly at hundreds of megahertz around the direction of the superconducting magnet field. If we have, say, proton and a carbon, they precess at frequencies that differ by 100 megahertz. You can put a mathematical proof on that, but it turns out that if the precession of L is at a very different frequency from the precession of S, then the transverse terms effectively just average out. So what you have then is 2 pi j Lz Sz, and that's called weak. And the strict mathematical condition for the strong coupling to be there is the difference between the Zeeman frequencies of the two signals must be smaller or roughly equal to the J-coupling between them. And for the weak, delta omega must be much greater than the J. And then these two terms no longer matter. So you can have strong J-couplings in homonuclear systems, but if you have very, very different chemical shifts, like aldehydes and methyl groups, occasionally you can see weak J-couplings even in homonuclear systems because the signals are just separated by so much. Right, let us now build the matrices for these operators and take a good look at what it does to those energy levels. Now I'm probably going to need another board for that, but yeah, I probably do. Okay, so let's do as much as we can here and then switch to the other board. Here we use exactly the same logic as here. We need operators that act with an X spin operator on the first spin and simultaneously with an X spin operator on the second spin. And so the structure of that, so Hj strong, will be 2 pi j and then Sz, meaning one of those, right, Kronecker with Sz again, plus Sx Kronecker with Sx plus Sy Kronecker with Sy. And let us build ourselves such a matrix. So, like that, 2 pi j, and then some space for matrices. Zz. We take this matrix, its first element, and multiply it by an instance of this entire matrix. So we are going to have 1 quarter 0 0 minus 1 quarter, then 0 0 0 0 0 0 0 0, and then minus 1/2, multiplying the entire matrix again, minus 1 quarter 0 0 1 quarter. This is the ZZ term. then plus 2 pi j, the xx term. Exactly the same. So 0, 0, 0, 0, then 0, quarter, quarter, 0, then 0, quarter, quarter, 0. That is the xx plus 2 pi j and the yy. And here we need to be careful not to mess up the signs. So 0, 0, 0, 0. And then minus I over 2 times that entire matrix. So 0. Minus I times minus I is minus 1 quarter. So quarter here. Then 0 there. And I over 2 times minus I over 2, that's plus a quarter. And then we have zeros here. And finally we fill in that part, and I think that's also a quarter here, and minus a quarter there. Okay, putting the entire matrix together and putting in the 2 pi j's as well, what we have is on the diagonal, so notice the ZZ term only contributes to the diagonal, we have pi j over 2. And then 0, 0, then another, so minus pi j over 2. Then those are all, well, let's just first draw that, and then we will add all the other terms to that. So put the zeros there, then minus pi j over 2, 0, 0, and then pi j over 2. That's the ZZ part. For the XX and the YY, that and that cancels. This is 1/2, so just pi j here and here. So that is for the strong. And if we have the weak J-coupling, then that and that term is not going to be there. Let us take a look again at our energy level diagram and look at how it gets updated when we take this into account. And probably I should just draw another instance of this somewhere here. Let's assume J is positive. Our top energy level has gone somewhat up. So the new energy diagram here somewhere, we have that energy. It is omega 1 plus omega 2 over 2 plus pi j over 2. So gone up. The second level has gone down. So what would have been, let's draw it roughly here, and then roughly there. That's the original location. And the second level has gone down, so like that. So that is now omega 1 minus omega 2 over 2, then minus pi j over 2. The third level has gone down as well, so we end up here. And that's minus omega 1 plus omega 2 over 2, and then minus pi j over 2. And finally, the fourth level has gone up, like that. And that is minus omega 1 minus omega 2 over 2, and then plus pi j over 2. And let us now think about what that did to our transitions. The first yellow transition, this one, that level went up relative to where it had been. That level went down, and so this gap has increased. So what we have here is omega 1 pi j over 2 pi j over 2. So this is plus pi j. If we look at the second yellow transition, this one, that level has gone down, that level has gone up, so the gap has shrunk. And so this transition is omega 1 minus pi j. For the blue transitions, what used to be this one has widened because that level went up and that one went down. So this is omega 2 plus pi j, and that transition has shrunken because that level went up and that level went down. So omega 2 minus pi j. And if we update our frequency diagram here, drawing it underneath for comparison, instead of one transition at exactly omega 2, we now have two transitions, one at plus pi j, the other at minus pi j. So we have a signal that has been split into two, and the difference between them is 2 pi j. And if we measure that in units of linear frequency, the difference is exactly j. And this is what you know from your organic chemistry, right? If you have J-coupled nuclei, then the signals split. Likewise, for the yellow transition, we have that one and that one. One is with plus pi j, the other with minus. And so we have here, likewise, two lines. And the difference between them is also 2 pi j radians per second, or equivalently j hertz. And this is why it's called J-coupling, and I'm sure in your organic chemistry courses you have all seen those Pascal triangle rules about how every spin you add to your system causes this additional extra splitting. This is where that splitting is coming from. Okay. Now notice that we've only considered the effect of the diagonal terms, so only the effect of the ZZ coupling. If we also consider these off-diagonal terms, the mathematics unfortunately gets a bit more complicated, and more complicated than we can handle in an undergraduate course in 45 minutes. But if we do account for those two extra terms, what is going to happen to that diagram is the following. You will have, again, the frequency, the amplitude. You will have those lines in those exact same positions, but the inner lines will get stronger compared to the outer ones, so it will look like that. And then the yellow transition here and here. And that is still omega 1, and that is still omega 2. And these are still 2 pi j and 2 pi j. But the intensity of the outside lines is smaller. This, for obvious reasons, if you draw a roof around here, it looks like a little bungalow. It's called the roof effect. and it only manifests if your difference between the two Zeeman frequencies is comparable to the J-coupling. And this gives rise to the common letter classification of spin systems. When two spins are close together in frequencies, we denote them by letters which are close together in the alphabet. And so spins that have that pattern of coupling are called AB spin system. And AB indicates that they're close in frequency. When we have weak J-coupling between spins that either are not even the same isotope or they belong to signals that are spread out in frequencies, we call this AX spin system. And then there are various intermediate classifications like ABX, which means that there are two spins that are close in frequency and one that isn't, or AX2, which means that this spin is there and there are two spins which are equivalent and far away from this spin A. So essentially the judgment to make when you're looking at such classification is, okay, how far the corresponding letters are in the alphabet, and that tells you whether the J-coupling is weak or strong between them. Okay, now the final thing to cover is the dependence of these J-couplings on the chemical structure. Very roughly speaking, the closer the two spins are together in the molecule, so the fewer bonds there are between them, the stronger the J-coupling is going to be, but there are notable exceptions. And that has to do with orbital structure. Essentially what needs to happen is the corresponding electronic structure theory orbitals have to overlap sufficiently for this interaction to propagate through the chemical structure. So to give you some examples, that's 3, so chemistry and J-couplings. If we have protons, things like this, so if you have C, then some R, R prime, H, then that's fairly strong. Depending on the system, that's roughly 10 to 20 hertz, depending on what substituents we have here. If we have systems like that, R prime, so H with free rotation around this bond, then that's roughly 7 to 12 hertz. However, exceptions begin when you start having double bonds and aromatic systems. So strangely enough, the J-coupling in such a system is only around 2 hertz. So this has to do with orbital overlap in the sp2 hybrid system here. And however, across, if you have, for example, that, so H, then H, and then say chlorine, and then bromine, a molecule like that, then it's around 20 hertz again. That is because the overlap is significantly stronger between the orbitals, which are in this case responsible for the J-coupling being there. If we have heteroatoms, they become significantly stronger. Typical CH, so HC J-coupling, so 13C, 1H, is of the order of 140 hertz. Weaker if they are aliphatic, so methyl groups. Stronger if this carbon is bonded to something with a double or a triple bond. In acetylene, I think that's nearly 250 hertz. So let's say that is a carbon that does that. A carbon that's double bond to something. Like that, that's 150. And then the triple bond carbon in acetylene, that's nearly 250 Hertz. And finally, if we go to things like d elements, where both the atom is very heavy, and so there's a lot of electrons, and also the spin-orbit coupling effects are strong because there is a spin-orbit contribution to this J-coupling. You can have things like platinum, so 195. Platinum has a spin half and 30% natural abundance, and if you have a platinum cluster, you can have things like 10,000 Hertz of the J-coupling between them. And I've given you a few more examples in the handout. Now, one important thing is that the dominant contribution, at least to the J-couplings in these CH&O systems, because it depends on the extent of orbital overlap, also depends on the dihedral angles that these groups have, which is brilliant because then it means that J-coupling gives you information about molecular conformations, which is super useful if you're into stereochemistry or drug design, because molecules that prefer certain conformations can be engineered to bind better to some receptor in some protein, and that is used a lot in pharmaceutical chemistry. So the final topic of 3b is Karplus curves. If we take your usual common carbon, have a hydrogen here, another carbon there, and a hydrogen there, then of course, because there's free rotation around that bond, you will have some plane in which that hydrogen is sitting and some other plane in which this hydrogen is sitting, and there will be the angle phi between those planes, and as you know, this is called the dihedral angle in that geometry. Turns out that if you plot the J-coupling as a function of phi, and I need to get my axis exactly correct here, so that is from 0 to 180, then if we have this angle equal to 0, that's of course a high energy conformation, right, the staggered conformation, but the sigma bonding orbitals in here will overlap strongly, and so you will have the J-coupling that's closer to the maximum range in here, so that's slightly over 10 Hertz typically, so here. Then if we go through 90 degrees there, then we would expect these orbitals to be perpendicular and therefore not overlap too much. And so that is reduced to just a couple of Hertz. And finally, if we go to 180, remember sigma orbitals don't just have the main lobes, they also have the tiny negative dimple at the back of them. That starts to overlap, and the J-coupling goes back up and actually can exceed the value that is there for the 0 angle, up to, I think that's roughly for a typical aliphatics about 13 Hertz. And this is super useful because if you have a protein that is well folded, then all of these dihedrals are either frozen in or they don't move too much. And of course, what determines whether the secondary structure of your protein is an alpha helix or a beta sheet or it is unstructured is precisely the dihedral angles between the consecutive bonds in the peptide chain. So it is possible by measuring certain carefully chosen J-couplings to actually find out by NMR spectroscopy whether a particular stretch of a protein is a helix or a beta sheet, and to some extent this information goes into protein structure determination process. Okay, I think that's all I wanted to say. So the summary of the lecture. I think if there's anything you carry away from today, it's this Kronecker product stuff. This will come everywhere in quantum mechanics. Some of you would probably go on to do some kind of quantum technology or artificial intelligence, and every time you have a multi-state system, quantum or not, interacting with another multi-state system, then of course every state of this one can correspond to every state of that one. So it's a combinatorial mixing of the two. Kronecker products are central to that process. You cron together the two state vectors, you get the state vector of the composite system. Because of this relationship, then whichever matrices you have that act on the two systems individually, you can compose operators that are global to the system, which are either designed to only act on one of its subsystems or designed to make the subsystems interact if you Kronecker together two non-trivial operators. And that mass is everywhere. This is, in general, it has a name, it's called a tensor structure. And it's quite important everywhere in computer science, including, unlikely things like machine learning. Okay, so using those tricks, we have, from our compiled list of elementary spin operators, built ourselves, firstly, the Zeeman interaction Hamiltonian, where that spin has one frequency and that spin has another. We Kroneckered one of our stashed matrices with the unit matrix that way and with the unit matrix that way to obtain the corresponding operators that act on one spin but not the other. We have got that matrix here. We had a look at it, and well, indeed, we have one line here and one line there, as befits two spins with different Zeeman frequencies that don't interact. Then we've introduced the J-coupling, and I've sort of given you a hand-waving explanation of why these terms sometimes don't matter if the frequency of spin L is very different from frequency of spin S. They simply move too quickly relative to one another, and this part of the interaction averages out. So if we're dealing with a nitrogen and a proton, or a carbon and a proton, or a carbon and a nitrogen, it's just a ZZ. Then we used the same Kronecker tricks to build the corresponding matrices. Took us some sweat, but we did it. And we have here, for the weak J-coupling, just the diagonal modification, so the energy levels drift up and down. And for the strong coupling terms, we have the off-diagonal things, which I don't have the time to consider in detail. What they simply correspond to is the change in the transition intensities in the end. But we decided to focus on just the energy modifications. We had a good look at what changes in the energy levels. Turns out that the outer ones shift up and the inner ones shift down. What it corresponds to the omega-1 frequency, now being two frequencies, one with the plus pi j, the other with the minus pi j, so the line splits. Likewise for the blue transitions, so the center remains where they had been, and they just split. And that's your typical pattern of J-couplings. If you add another spin to the system, you will have further terms in this Hamiltonian and extra splittings every time a new spin is added. And the splitting is into two lines, so these two will split into four. If the middle ones overlap, you will have the classical 1-2-1 triplet, and this is where all the patterns that you've learned about in organic chemistry strictly quantum mechanically come from. Finally, of course, the first thing organic chemists do once they've cooked something is to make sure that it's actually what they want. And then they run an NMR spectroscopy on it, and different structural fragments have different J-couplings. There are giant books and review papers that tabulate all of this, that allows you to confirm the structures that you have. And one of the important and useful in structural biology in particular property is that these 3 bond J-couplings, they depend on the dihedral angle over the 3 bonds that are involved in there, simply because the J-coupling depends on the extent of the bonding and antibonding orbital overlap. So at 0 and at 180 you have maxima, and at 90, when the orbitals are perpendicular, you have a minimum. That's it. Any questions?